How am I going to do this? This would be impossible online, and it's going to just be pretty damn difficult in person. All right. I need group one. Branson, McKenzie, Marcus Blake, not everybody's here. I need you guys to be up here. Mary, can you get up and move someplace else? I need your chair spatially. Sorry. Actually, Mary, sorry. Can you move to the very back? It's just going to be a little easier to arrange this. Marcus, can you come to one of these seats up here? Yes. You're with Benton, McKenzie, Marcus, Blake. You guys are all up here. All right. Olivia, this is group two. Remind me, your name? McKenzie. Sorry, it's a mask. So you're with them. So you need to be at one of those two chairs. So weird to not see you guys all semester. Yep, up there. Yep. All right. That is that. Winston. Mary. Actually, I'm going to probably ask you to move again. Just remind me of your name. Jackson. You need to be with group two. So you're with Olivia. Olivia's here. Olivia's here. You guys have been studying together. You guys should be connected. Okay, Mary. Come and be with Winston. And Kenton's not coming, so he's going to chime in via Zoom. So if you two could get on Zoom, that would be great. Nobody else needs to be on Zoom, obviously, because we're clearly here. All right, so leave your chairs where your chairs are, but turn your chairs so that you can face the people that are in your group. Normally, I would have you huddled up on one another so that you're all working around like a common table, but obviously we are not going to be able to do that now. Because we can't. All right. Take these, leave them face down on your desk or on the floor next to you. You'll need them later, but you don't need them now. And I don't want you to see them now. Same thing with you guys. Don't look at these yet. Don't look at these until you're asked to. And the other problem is this requires at least 9 people. And unfortunately, we have that many, but 1, 2, 3, 4, 5, 6, 7, 8. We don't have 9 people. So that's tricky. So keep these covered until it's time. Okay. Hey, Winston.
Yes.
No, not Winston. Kenton. Is Kenton? No, it's just Winston. Where's Kenton? Winston, you just logged on?
Yeah, I'm on here.
Okay, all right, that's what I heard. Okay. All right. At Polyface Farm, there's basically a food web that is being employed to basically allow Joel Salatin to essentially make all the animals do most of the work. And the way he does this is by essentially kind of leveraging the capabilities of each of the different farm animals to do a particular task. The cows keep the weeds cropped down, keep the vegetation cropped down. The chickens come through and do insect control, all the while adding nutrients and spreading around those nutrients, et cetera, et cetera. And so he's using this thing called a food web. And a food web is just a graphical representation of energy and nutrient flow through an ecosystem. Usually we think of it as energy flow through an ecosystem. So it's a graph that shows the energy relationships between organisms. And when I was first introduced to these back in public school, you would oftentimes see like, you know, a stream, and in the stream were little phytoplankton, and then the phytoplankton were being eaten by a little fish, and then the little fish were being eaten by a bigger fish, and then there was an eagle swooping down, talons outstretched, coming down and grabbing the big fish. And it's basically just showing energy flow moving from one place to another in this ecosystem. Well, the same thing happens at Polyface Farm. The grasses absorb energy from the sun. They use that for growth. The cattle eat the grasses. They poop out the cow patties. Flies come in. They colonize those cow patties. The chickens come in. They eat the larvae of the flies. The chickens poop down more fertilizer that feeds the grass, et cetera, et cetera. So this exercise here is an exercise that I picked up a number of years ago, and it's about a food web. But it's about a food web, and you're going to learn about this food web through looking at figures from a paper. This was a paper that was published in Science, I think back in 2004. So it's good science. It's published in one of the best journals out there. And so the way that this is supposed to work, assuming that we had at least 3 people in each group, is there are 3 figures in the paper. So group 1 has figure 1. That's you guys up here at the front. Group 2 has figure 2. Group 3 has figure 3. You guys at the back. Your goal here at the beginning is to understand figure 1, figure 2, and figure 3 to the best of your ability. Understand it as completely as you can. I'm going to be walking around the room, asking questions, answering questions, et cetera, et cetera. Once all three groups have their figure firmly in their minds, we're going to move people. One person from group 1 is going to join group 2. Everybody has all three figures in their possession, so you don't have to carry figures around with you. They're already there. You just have to carry your figures that you possess with you. Somebody from figure 2 is going to go to figure 3's group. Somebody from figure 3 is going to join figure 1. So the person from figure 3 has their figure 3, and the people from figure 1 have already understood their figure 1. So it's a responsibility of people in figure 1 to teach their figure to figure 3 person, and it's a responsibility of figure 3 person to teach their figure to the figure 1 people. Same thing here. People who are already here teach their figure 2 to the figure 1 visitor. Figure 1 visitor teaches their figure to the figure 2 people, vice versa. Once everybody in your group understands the 2 figures, we'll do it again, but now figure 1 will go to figure 3. Somebody from figure 2 will go to figure 1, and somebody from figure 3 will go to figure 2. I'll redraw the arrows when we get to that point. Same thing happens. The visitor teaches their figure, which is new to the group, to the rest of the group, and the rest of the group teaches whatever figure that person hasn't been exposed to, the figure that they have that that person hasn't seen before. Once you finish this, your task is to draw the food web that is represented by these figures of data. I'm going to tell you, though, that the paper is not about any of the organisms in any of these figures. So an additional task is for you to figure out what the paper is actually about, because the paper is about the things that are in the figures, but the paper is also about some bigger thing that's not in any of the figures. Trust me, I've done this a gajillion times. You always figure it out eventually. Everybody clear on what the goal is? Start talking to one another. Before you talk to one another, you might want to read through the figure legend, do your best to understand it individually, and then after you've looked at it yourself, start talking to your peers with it. Yeah. Kenton was on. Oh, I thought Kenton was on. Yeah, stay on just in case, but let me send Kenton an email. All right, I just emailed him. Sorry, you guys are so spread out. Did you vote this year, or is that from another year? You guys have one of the most complicated ones to begin with, so take your time working through it. It is a puzzle, actually. This teaching technique is a technique called the jigsaw, where you give the class different pieces of the puzzle and you ask them to create the final image of whatever it is. Yeah, think of it as population size, a measure of population size. So why is the mouse population going down in some cases? So in one case, they're being removed. What's the other situation that's leading to mouse declines? Yeah, they're just going into winter, yeah. Yeah, so pay attention to what's on the x-axis. That's especially important for your group because your group has a timeline, so the x-axis is super important. What are you looking for? Okay, so all you have in this figure is you know when acorns were added, right? And they were only added in certain places, right? They were only added in the experimental plots. So when were they added? Yeah, November, December, yep. Oh yeah, October to November 95. Yep, yeah. So that's what those arrows indicate. Arrows indicate when acorns were added, and the acorns were added only to the experimental plot. So what did that do to mouse numbers? So all mouse numbers declined, but what happened to the mice in the experimental plots? They declined, but they didn't decline as much. Yeah. So they all decreased, but they didn't decrease as much. How are you guys doing? Okay, great. That's the first step to understanding. So what's confusing to you? Okay, so tick densities. The way you would find tick densities is you would collect a bunch of mice, count the number of ticks on them, and then however mice per meter squared there are, however many ticks are on those mice, that number of ticks per meter squared is the density. So it's expressed in lateral ticks per meter squared. Okay? So on the control grids, there are relatively few numbers of ticks, but on the experimental grids, there are a lot more ticks. So then the question would be, are there more ticks on the experimental grids because there are more mice on the experimental grids, or because there are the same number of mice, but each mouse is carrying more ticks? So that's what figure B is about. Is it because there are more mice on the experimental grids, or because there are more ticks per mice on the experimental grid? Are those two figures statistically different from one another? Yeah, they're just right on the very edge of being different. So they're just slightly different. So it isn't that there are more ticks per mouse, because those are pretty similar, just barely crossing the threshold of statistical significance. And so it must be that there are more ticks per meter squared because there are more. Finish the sentence. Hold on. I'll come back to it. Hold on. I'm drawing mice. Okay, mouse group at the back. You have 4 mice. Each mouse has 1, 2, 3, 4. Each mouse has 14 ticks, or 4 ticks rather. And so 4 ticks times 4 mice, that's 16 ticks per meter squared. So you can have that. You can also get 16 ticks per meter squared if you have half the number of mice. But in order to do that, you have to have twice as many ticks per mouse. So you still have 16 ticks per meter squared, but the density of ticks on each mouse is higher. So you have more ticks per mouse and more ticks per meter squared, as opposed to having more mice, each mouse with fewer number of ticks. So that's what those two figures are trying to get at. Is the increase in the number of ticks per meter squared due to there being more ticks per mouse, or just having more mice? And the answer is having more mice, yeah, because the number of ticks per mouse isn't really that different. Yeah. Wait, so what's the difference between the control grids and the experimental grids that might have relevance to mice? Yeah.
Okay, so this one's talking about the control grid.
Uh-huh.
And the gypsy moth, the tree, and the larva produce.
Okay.
And
Yep.
then we don't understand the difference between the control grids and the experimental grids.
Okay, so what does it say in the figure about the control grids and experimental grids? Control grids before mouse removal.
And then the bands of the trees.
So what did they do in the controls and the experimentals?
What?
They removed mice. So, and then what else? Yeah, so in the experimental grids, they would have removed mice. The control grids you leave alone.
Okay.
Okay? So that's the manipulation that they're talking about between these two types of plots. Control grids, they removed mice. A, B, and C occur at different time frames, and it tells you that in the figure. So I would write up next to the figures what the times are that A, B, and C come from. That'll help you understand the figure a little more. Now that you know what the difference between control and experimental is from this standpoint. Yeah, a masting event is a when the trees create a huge crop of acorns, and they fall to the ground. They provide food for things, and typically when they mast one year, they've used up all their energy that year producing all those acorns, such that the following year they don't have many acorns at all. Yeah, because nobody's doing anything to anything until they remove mice right there. And what are those the black bar and the open bar? The black bar is the removal of the mice, and the open bar is when moths are pupating, right?
Here, and then it goes down before.
Yeah, but this bar and that bar.
Oh,
You guys didn't even notice that bar?
okay.
There's a, well, okay, so it's in the figure. The black bar represents when they removed the mice, and the white bar represents when the gypsy moths are pupating. White bar, black bar. Is it becoming any clearer?
Kind of. So like this one is late stage larva. This is the number of females supply it, and then this one's the number of eggs. This is after the mouse removal.
And is this before or after mouse removal?
I think it's before. No, it's
B?
after mouse removal.
After mouse removal. And what is A?
Before.
A is before mouse removal. So if these are larvae, where do larvae of butterflies live? Butterflies and moths eat what? What part of the plant? They eat the leaves. So these larvae are not at the base of the tree. They're up in the canopy of the tree eating the leaves. When they pupate, what do they do? Where do they pupate? Nope. Not these guys. Did they mention something about burlap bands? Why did they put burlap bands around the trunk of the tree? No. If you're living up in the tree canopy and you're eating and you go to pupate, generally they pupate in the ground. So to get to the ground, what do they have to do? So how do you get out of the canopy of a tree? You crawl down the what? In the trunk. And they put these burlap bands around the trunk so they could do what? So they could what? No, so the researchers could sample them. They crawl under the burlap strips. They're comfortable in there. It's nice and warm and moist. And then they can pull the bands off and get a census of how many are there. Then they pupate on the ground. When you're on the ground, though, what are you susceptible to? Maybe mice killing you and eating you because you're unprotected because you're in this pupal case. So were the experimental and control grids different in terms of the number of larvae?
This one and the band removal.
Really? Because it looks here like, yeah, that's not really different at all. That's not really different from that. That one's higher, but on average, these are no different than these on average if you average across all of them. So there's no differences here. What happens here, though? On the control grids, you have many fewer pupae than you do on the experimental ones. And in terms of egg masses, which is the adults after you pupate, you emerge into an adult, you fly up into the tree, and you lay eggs. There are many fewer eggs in the controls than in the experimentals. So by removing mice, you got no more larvae, but you got more pupae and you got more egg masses, right? So obviously, the moths must be somehow correlated with, must be having an effect on the moth, because, they say that right, squirrels are having an effect on the moth, because when you get rid of the squirrels, the number of moths goes up. Squirrels, why am I saying squirrels? Mice. So get rid of the mice, you have more pupae, you have more adults that then lay more eggs. Leave the mice in place, you have lots of larvae, but when they come down to the ground, they're clearly getting killed by the mice. All right, how are you guys doing? So masting event followed by mouse removal. Mouse removal resulted in a reduction in the number of mice, but this only occurred on the experimental grids, right? Then they went back up as soon as they stopped removing them, right? Then winter comes, and what happens to everybody? They all drop, except for the experimentals, because what did they do different on the experimental plots? They added acorns, so they dropped, but they didn't drop as much as when they didn't add acorns. Is there anything else you need to know about that figure? There's nothing in here about the moths, is there? Or is there? Except just when the moth pupation occurs. So they coordinated their mouse removal at the time that the moths are pupating. And so while you may not understand the significance of that now, you will here in a few minutes. Any other questions about the figure? Tick group at the back, you good to go? All right, one person from each group. Figure 1, send a person to figure 2. Figure 2, send a person to figure 3. Figure 3, send a person to figure 1. This is figure 1, that's figure 2, figure 3 is at the back. So one of you guys come to the front. What? No, you can, or you can just bring it with you, yeah. Or just set it down. I don't know what happens to tension. Your jobs are you guys teach her your figure, you teach them your figure, vice versa, everywhere. They should have, everybody should have all 3 figures, but they need to look at the figure that you're bringing. So you're bringing figure 2, so you need to now look at figure 2, and you need to have brought all your figures with you. Yeah, you need to carry your figures with you so that you have them. You look at whatever figure she has, which is figure 3. And she can look at figure 1 now. Can you hear them okay? Do you want to move your chair up here? You'll be a little closer, but you'll still be 6 feet away. Actually, just move this chair. Leave that chair where it's at. You can sit there and I'll stay away from you. See, you sent away the person that you thought understood it best, but then that left you guys with the necessity to teach her. So now you have to make sure that you're clear on it as you convey it to her. This is actually the brilliance of this method. That was quick. Or you're just really good at explaining things? Okay, all right. How are you guys doing? Okay. Okay. Yeah, so if you want to, you can start sketching the parts of the food web that you currently understand, because you now have two pieces of the puzzle. You have information about ticks, and you now have information about moths. What you don't have is much information about mice, although you have some information about mice. So you guys are best equipped to understand new information because you have the timeline of the experiment in front of you. And she's adding to your timeline by giving you now some information about another species, but it occurs relative to things that happen in the timeline that's in figure 1. Does that make sense, Mary? So you should be trying to put information from figure 3 into the context of when things happen in figure 1. Because you know you're building a food web, and now you have a little more information than you did with just a single figure, you can begin putting together a food web based on the things that you know from the couple of figures that you have gotten. You'll fill that food web in with the next figure that you get, but you could start a rudimentary web right now. Yeah, sure. No, you're going to keep these. You're going to take these with you when you're done. So who are the ticks feeding on? They're feeding on the mice. Who are the mice feeding on? Acorns and moths both. Who are the moths feeding on? You don't know yet, but you will. I mean, but generally butterflies and moths feed on what? They feed on leaves, plants, yeah, leaves of plants. So what's the only plant that anybody's mentioned? So who masts? Nope. Nope. Trees. So acorns. Acorns are produced by what kind of tree? Oak trees. So they're oak trees that are producing acorns, and so presumably the gypsy moths are feeding on the oak trees, the leaves of the oak trees. So you're starting to put together something of a food web. Who are the players in this web? And then the trick is just figuring out what the relationships between each other are, and if you change the abundance of one, what does that have on what effect does that have on all the other members of the community? All right, do you feel you understand your two figures that you have before you adequately? All right, someone from figure 1 needs to go to figure 3's group. Someone from figure 2 needs to go to figure 1, and someone from figure 3 needs to go to figure 2. It can either be people who have moved in the past, or it can be a new person moving. And I realize for the groups that only have 2, that means it's all going to fall on one person to do whatever explaining still needs to be done. All right, 1 go to 3. 2 go to 1, 3 go to 2. Wait, Only one person from each group moves. So if Mary's moving, Marcus doesn't need to move. Wait, everybody go back to your groups. Everybody go back to your groups. Nope, where you just were. Mary? This is group one. You guys need to send one person. It can be Mary or it can be somebody else. You need to send them to figure 3. No, sorry. So everybody sit down. Everybody sit down. Everybody sit down. Everybody sit down. You guys have at your disposal figure 1 and figure 3, right? Figure 3 does not have at its disposal figure 1. It has figure 2 and figure 3, right? So they need somebody from figure 1 to go to figure 3 and explain figure 1 to them because neither of them have seen figure 1. Doesn't matter who it is. It can be Mary. You can send Mary back to her old group because she has figure 1 and figure 3. She hasn't seen figure 2, but figure 2 lives back there. Okay, so it doesn't matter who. It's just that one person from what is now figure 1 needs to go to 3. One person from what is now figure 2 needs to go to figure 1. And one person from figure 1 needs to come to figure 2. So actually, it would be better if it was somebody who hasn't moved yet to move now. So if you've moved, stay in your group. If you haven't moved, one of you move. This is always the most confusing part of this, is how to move. Can we join figure 2? Huh? Wait. What did I do wrong? Oh, wait. Sorry. Go back to your groups. Go back to your groups. Figure 1 goes to figure 3. Figure 3. Figure 2 bypasses 3 and goes to 1. Figure 3 bypasses figure 2. Yeah, this is right. So if Marcus goes to figure 3, you're bringing 1. Okay. Sure, we can do that. Sure. All right. Everybody go back to your original groups. This is way easier when you have more people, actually. All right. So now every member, every group should have representatives of all 3 figures, and everybody is about to see figures that they haven't seen before, right? Okay. So you haven't seen 1 at all. Yeah. And you haven't seen figure 3. Did you break it or just misalign it? Ah, nice. What's up? Oh, you can ask me. What's up? This is why we have you teach one another, is because it forces you to recall it and teach it over again.
So,
And this is the one that you were exposed to second, so
yeah.
it's the one you're least familiar
Yeah.
with. Okay.
So this changes drastically, and this kind of stays the same.
Yeah. So what's happening according to this figure between control and experimental groups?
So would be now the acorn, right?
These are acorn editions. Yep.
Yeah.
So acorn editions in October of 1995. So maybe it would be better for, is this where you're starting? Olivia, you have figure 1, right?
Yeah.
You haven't seen figure 1. It would be better for him if you expose him to figure 1, because that then allows him to put his figure in time context. Yep. But that only happens on the experimental grid. So be sure that you're keeping experimental and control. So experimental are the black circles, controls are the open circles. Did you go through figure 1 with him? Okay, all right. It's easier if the person with figure 1 to a new group leads with that, because that gives them the timeline. So this is this graph is a response to acorn addition, right? Yep. So where is that in the timeline on figure 1? That happened in fall of 95, and so these numbers are coming from spring of 96, right? In figure 3. So
yeah,
tick densities after. Yeah, so it's in August of 96 is when they're taking these data. So it's towards the end of the experiment. In that period, what's happening to mouse density on the experimental grids? On the experimental grids, relative to the controls, you have figure 1 in August of 96. But for months now, you've had what on those experimental grids? They declined, but did they decline as much as on the controls? No, so you have more mice on the experimental grids because of the acorn additions, presumably. So the question is, why do you have more ticks per meter squared? Is because you have more ticks per mouse, or do you have more mice, is the question. That is what I was explaining there. I usually do it in the form of a image. So I would just put names in a way that allows you to draw arrows. The arrows are then the direction of energy flow. So who's getting energy from whom? Who's feeding on whom? So oak trees are putting energy into acorns. Who's eating acorns? Mice are eating the acorns, et cetera, et cetera. So energy is leaving acorns and going into mice. Energy is leaving mice and going other places. But make sure, before you start drawing a figure, make sure that you understand and have fully integrated all 3 figures with one another. Because if you haven't done that full integration, it's going to make drawing a food web harder. better to spend more time on the figures and less time drawing the figure. You guys don't need to be paying attention to this. You're supposed to be drawing a food web, aren't you? So remember that the other thing you're supposed to be doing is once you have a food web, you're supposed to try and figure out what the paper is really about without looking at the PowerPoint. Do not open up this PowerPoint on your computers before we get to the end. think you have food web done? Okay, is gypsy moth energy flowing to trees, or is tree energy flowing to gypsy moths?
I guess the tree energy from
And is the energy in gypsy moths flowing to mice, or is mice energy flowing to gypsy moths? Yep. Remember that in food webs, the arrows represent the direction of energy flow. All right, who wants to put their food web up on the board? Go for it. Huh? Do whatever. Yeah. Erase that arrow. Give yourself some space. Okay, so this encapsulates everything that is in these figures so far, right? So if we look at figure 1 up here, at the very beginning of this experiment, mice numbers are increasing overall, right? Why? Because of the masting event. Because mouse populations are increasing due to the masting event, that tells you immediately that what are mice feeding on? They're feeding on acorns. So energy is flowing from acorns to mice, and because acorns are the fruit of oak trees are dumping a lot of energy into acorn production. That acorn production then produces a response in the population size of the mice. Then on the experimental plots, they removed mice at the same time that pupae of the gypsy moths were pupating. They timed that precisely because they want to see what's the effect of reducing mouse populations on the gypsy moth population. Where does that information appear? It appears in figure 2. These are gypsy moth larvae. Where do the larvae live? Up in the treetops. Then when they go to pupate, the larvae do what? They crawl down the trees and pupate in the ground. When they get down to the ground, what are they susceptible to? Predation by mice. So before the mouse removals, there were lots of larvae in the trees. After the mouse removals, though, the controls, where there were no mice removals, the number of pupae went down. They didn't in the mouse removal plots, experimental plots. Egg masses per tree the following spring are lower in the control groups, once again, because there are a lot of mice on the landscape. More where you remove the mice, because where there are no mice, the pupae survive, the pupae emerge as adults, and they go on to lay egg masses. And so by removing mice, you increase the gypsy moth population, right? So now we can start putting some directionality on this, right? If it's a good year for oak trees, they produce a lot of acorns. If you produce a lot of acorns, what do you also produce? A lot of mice. And if you have more mice, what happens to gypsy moths? It has a negative effect on gypsy gypsy moths. So there's this directionality. More tree, better trees, more acorns, more mice, fewer moths. In the experimental groups, you removed mice. This is where you left mice alone. More mice means fewer gypsy moths. Then in the winter, they added acorns to the experimental plots. What did that do to mouse numbers during the winter? They went down, but they didn't go down as much as on the control plots where they didn't add acorns. Once again, indicating this link between acorn abundance and mouse population sizes. And then when did they measure ticks? August of the following year. And so now my computer's way far away. So figure 3 looks at ticks. This is all from August of '96. The number of ticks per meter squared is much lower in the control plots than it is in the acorn addition plots. Acorn addition leads to more mice. The number of ticks per meter square is higher, but the number of ticks per mouse is not higher. So if you have the same number of ticks per mouse, but you have more ticks overall, that's because you have what? You have more mice. It's just a function of the number of mice. So you add acorns to the plots, that raises mouse numbers above what they would normally be at the end of the winter. You get more, more ticks per meter square because you have more mice. So what's positive for acorns ends up being positive for mice. What's positive for mice ends up being positive for ticks. But what's positive for mice ends up being negative for gypsy moths. And that ultimately ends up being a good thing for oak trees because gypsy moths, there are fewer gypsy moths, less herbivory on the leaves of the oak trees, and they can produce more acorns the following year. There's another set of arrows here. If it's a bad year for trees, that ends up being bad for acorns. If it's a low year for acorn production, you end up with fewer mice. You end up with fewer mice. You end up with fewer ticks. But if you have fewer mice, you end up with more gypsy moths, which ends up being a bad thing for trees because the gypsy moths eat the leaves off of the trees. So this is how a food web works. What happens at one level in a food web can have either negative or positive consequences for what happens at another level of the food web. So as one thing goes up, the other things may go up or go down depending on what the relationship is between them. So this is a article that appeared in journal Science. Science is one of the top journals in the world for publishing science. Why on earth would Science have published this article about gypsy moths and mice and oak trees and acorns? What is this paper really about? Why would anyone care about a food web in a temperate forest? And by anyone, I mean humans. What disease do ticks carry? This is a paper about Lyme disease. Because if you have more acorns produce more mice produce more ticks. There's also deer is in here, but it's not in this paper per se. But more ticks ends up meaning more Lyme disease. And so if you want to predict incidences of Lyme disease in the northeastern United States, all you have to know is what is acorn production like the previous year. If there's a big acorn masting in the fall of one year, that's going to increase the mouse populations that survive over winter. That's going to lead more ticks available the following summer, which is going to lead to a higher incidence of Lyme disease. If you have a year with low acorn production, you have fewer mice, you have fewer ticks, and you will have less Lyme disease the following year. Deer also feed on acorns, and ticks also feed on deer, and so the same dynamic plays out with deer as well. So if you have more acorns, more deer, more ticks, more Lyme disease. So the reason that they did this food web analysis was they wanted to understand what the controls were on the incidence of Lyme disease. Lyme disease ticks up some year and ticks down other years. Well, what's driving that ecologically? Well, what's driving that ecologically is a food web that was acting for a full year previous to the outbreak of Lyme disease. So if you can predict what's going to happen with Lyme disease a whole year in advance based on production of acorns by oak trees the previous year, you can basically advise people, don't go out to the forest as much this coming summer. Or if you do, dress appropriately, put sulfur around your legs, tuck your pant legs into your socks. Just be more cautious about getting ticks on you and allowing those ticks to actually dig in and start sucking blood from you. Because if you know that Lyme disease is going to be on the increase, you know that tick numbers are going to be on the increase, if you do go out into nature, you can take appropriate precautions, and as a result of that, reduce the incidence of Lyme disease. But that insight into Lyme disease was totally based on a very ecological idea, this idea of food webs. How does energy flow from one group of organisms to another group of organisms? And in this case, what are the human health consequences of that? But this is just one particular application of food web. On Wednesday, what we're going to do is we're going to talk some more in detail about the food web at Salatin Farm. So if you haven't read the chapter on practicing complexity, that's the chapter where they're really talking about the food web and how Joel Salatin's farm works. But this is hopefully an introduction to the idea of what a food web is and how it works in nature, so we can look at a farm, which is basically just a food web as well, and see how those things differ. All right, thanks for coming. I will see you on Wednesday.